Quanto sta distante? Perché se lo attacco qua forse non è ma... Va bene? Attacco così funziona?
Sì, sì, ieri andava bene.
Ok. Questo lo mettiamo qua. Metterci anche. Allora, lunga la registrazione. Sì, sì, sì. Se ieri Massimiliano aveva una voce abbastanza bassa e abbiamo provato a aumentare la spia lì, ma... Ah, ok. Sì, 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 no. Non c'è problema. Ok. Alle 10, la pausa 10:30. Ah, 10, quindi tra un'ora. Proprio c'è il tempo di iniziare e ci fermiamo, va bene, ok. Ok. Okay, so good morning everybody. I'm Pietro Bonfa from Cineca, and I've been asked to introduce some programming models for accelerators like CUDA, OpenACC, etc. So as you can imagine, this is quite a lot of stuff. So I've been told that the audience hasn't already deepened this topic. Is it true? I mean, how many of you already tried CUDA, OpenACC, or stuff like that? Okay, fantastic. So no one will be bored by the lessons of this morning. So the idea is to have a very interactive lesson. This is a presentation. Morning. So okay, before we do anything, I'd like to kind of I know it cannot work if I don't plug this in. Meantime, everybody finds a place. And now it works. Fantastic. Okay, so the idea is to use these few minutes to bootstrap. So I hope that everyone here in the room has an account or a way to access Galileo. That's where the GPUs I will be talking about are, and that's what we'll use for today. So you should all be able to log in into Galileo. You should all know how to load a compiler in Galileo's environment. Is this true? No? Someone saying no? So no for point 1 or point 2? Point 2, fantastic. But that's cool because I also have to introduce another thing. I will be using new compilers to avoid some bugs in old compilers, especially PGI. So I want to briefly introduce. Maybe you cannot see anything if the screen is too small. It's more like this. So select font. let's do something like this. This should work. And then? Oh, well, let's do like this. Oh, it's horrible. Well, options, select font. Let's choose another one. Something which is fixed. Well, let's see what happens with this. Well, a little bit better. I'll change it later. So I log in on Galileo. Oh, this is awful. Okay, fine. So you know you can do module load. I think you cannot see anything because it's where I am. So if I do like this, probably you see something more. So you should all be able to log in, and you should all be on Galileo right now. So you then do module, for example, available and GCC. Well, it's probably GNU. And you get the compilers. In this case, module gives you GNU 6.1.0. But that's not the only compiler that we have. To show all the compilers, you have to do something like module load profile global. Okay, can you see it? Hope so. And now if I repeat the command I did before, module available GNU, there's something more. Well, they are pretty old, but the important thing is module available PGI. I'll repeat this later. So, and you see that you have a number of PGI compilers that you probably couldn't see at the beginning when you logged in without doing profile global. So the same holds true for CUDA that we will be using today. So again, since I'm already using the terminal, I'm showing that you have to do profile global. And to show the CUDA toolkit, you have to do module available CUDA. And that's it. Everybody up and running? Fantastic. So I can go back to the presentation. Okay. So 1, 2, 3, done. Point 4 is getting the hands-on for today. The link is also on the page of the school, the one in Cineca, learn.cineca.it, or you can copy-paste this link from the slides. No, sorry, this slide is the Bootstrap slide, so I don't have it. But the link is on the web page of Cineca, or we can do it later. I will also show you another link later on. So, first step is discussing the problem when we want to tackle today with GPUs. So it's autumn, so leaves fall on the ground, and the first thing you ask yourself is, what is the area that leaves cover on the ground when they fall, and how does this evolve? So I have a background in physics, so I generally work in the approximation of spherical horses in vacuum. So the problem of leaves turns out to be the problem of finding the area covered by a number of circles that more or less look like this. They may be overlapped. And it's pretty nice that on Rosetta code you have this problem already solved. You have it solved in C. I will be mostly showing C code today. Someone is uncomfortable with C and only does Fortran. It's very simple C, so not much. And you may as well convert the examples in Fortran. I would be grateful if you do so, so I can just steal your code and put it into the repository. So a few things on how this is done. This is done with a Monte Carlo sampling. I think you already know that, but the idea is to create a box and then start with a uniform sampling of this box. So you have to generate a huge number of random uniformly distributed numbers along x and along y. This is proved to be a uniform distribution in these two dimensions. So what we'll be doing is just throwing at random points in this box and checking if the point is inside or outside a circle. And this multiplied, so the total number of points inside divided by the total number of points that you throw, multiply the size of the box, will give you the area of the surface that is shown here in the side of the box. Clear for everybody? Pretty simple. So if you look at the code here, hope you can see is Rosetta code, and then you can just look for total circles area, Monte Carlo sampling. You'll see that this code is more or less the opposite of what I will discuss today. So it's a serial code. It runs on one CPU, and what it does is the most obvious thing you may think when you have to do in C the algorithm that I just mentioned. So get a random point, put it inside this box, check if it's inside and outside, and then move to the next point. Our task for today is to change this approach and make it, let's say, change it in a way that can be successfully used on a GPU, which is a device for massively parallel simulations. So this concludes a pretty long bootstrap, and so I can move to the first presentation, which is oops. Okay, voila. Okay, so what is heterogeneous programming? So the definition is taken from Wikipedia, as usual. You can gain performance and energy efficiency. Honestly, more often than not, this or is a and, by adding different types of processor or so-called coprocessor accelerators that are specialized for doing a particular task. If you look at the top 500 computers, you will see that the first 5 or so, I'm not sure, but certainly the first 3 supercomputers are using accelerators to obtain the theoretical peak performance and the measured peak performance that they are ranked for. And so most of them, not all of them, but most of them use general purpose graphic processing unit. What are general purpose graphic processing units? Well, it's a GPU, so a graphical processing unit, where you also have a set of instructions that allows you to perform some operations that are not very relevant to graphic computing. So, for example, double precision operations is something that you generally don't care much when you are programming for textures for a game, but you do care a lot when you're doing scientific computing. And so when you want to run a scientific code and you want to take advantage of a heterogeneous system where there are graphical processing units, you must be sure that the hardware, the architecture that is installed allows you to perform the type of simulations that, the type of operations that scientific code does most. And this is more or less how the acceleration takes place. So why are GPUs somehow faster than CPUs? Why are we using GPUs to have accelerated supercomputers? Well, this is just a sketch of how the thing is. One may say that the main difference is that there is a design which is strikingly different between the CPU and the GPU. So you really have more transistors, more hardware, more cores devoted to data processing instead of controlling the pipelines and doing speculative execution or optimizing memory accesses. So this is more or less how the GPU provides you much better performances than the CPU. But what is the cost of doing this? Well, of course, is the fact that what the CPU does for you is moved to the programmer's work. So it's your task to schedule the data movement, the data processing, and to do a lot of optimization that on the CPU, a good compiler and a good processor and a good pipeline scheduler will can do for you. So this is the object that we will be using today. It's a quite old device. It's an NVIDIA K80, and it actually has two chipset, two GPUs per device. So you do see for one K80 you actually see two GPUs because both of them are connected to a PCI Express switch, and both the chips have 12 GB memory. So you have 24 GB memories on this device, and this is the bandwidth that you obtain for the two sockets, and each of them is has 15 multiprocessors. We'll see later what this is, and 192 CUDA cores per multiprocessor unit. So it adds up to 2088 CUDA cores. So you immediately see the difference. We are used to tens of cores on the CPU. Here you have thousands of cores. But each of these core has very low frequency. And so you have to be careful, of course. Whenever you are doing something sequentially, so whenever you are using a single core, you're doing the operation very, very slowly. And the advantage comes from exploiting as much as possible all the CUDA cores of the GPU. And this is how the architecture looks like. And you can see the streaming multiprocessors, and you can see the memory controller that controls this L2 cache, which is also called global memory. And we can have a look inside, and this is what a streaming multiprocessor looks like. So I don't think you can read anything, but Just stay with me while I tells you what the green and orange boxes are. So in green and orange are the actual units for doing the arithmetics. So green are the single precision unit, orange are the double precision units. So you can immediately see that the ratio between green and orange here is 1 to 3. And this tells you an important detail of this CPU. The ratio between double precision and single precision. You may find other GPUs where this ratio is very different and is much more towards the single precision. These are, of course, GPUs that are not well suited for scientific computing. So whenever you are approaching an accelerator system or a GPU, be careful and check this before trying to obtain acceleration. There are a number of other elements in this picture, like load store units that load and store data from the global memory, from the DRAM, and there are special function units that are meant to execute, for example, transcendental extraction line, sine, cosine, square root, and these are extremely fast. So this makes computation of this kind of mathematical function extremely cheap on the GPU. So if you're uncertain about loading data or recalculating it, if it's this kind of operations, probably it's better recalculating what you already store somewhere. Now I would like to briefly show two commands that are very important for today, and these are the two commands that you should run on Galileo. So if you still have a login shell, you should be able to run NVIDIA SMI, and you may do this on the login node. And this is a sort of top of for the GPU. So how many GPUs do you find on the login node? Anyone able to run the command? Two GPUs, and it should be there also the type of the GPU. K40, right. So it's different from the one that I told you. It's a version of a version with a single chipset. So you do see two GPUs because there are actually two K40s installed on the login node. If you want to try, you may go to one of the compute nodes. And have you been introduced to the scheduling system? I think so. Not sure if you know how to access GPUs, but I think you, with the reservation that you have, you should always get a node with the GPU. If someone is kind enough to try to submit an interactive job and check what is the output of NVIDIA SMI on a compute node, I can do it at the same time, but maybe I do it here, otherwise I don't see anything. Device not found. So that means that you are not running on a node with a GPU. So let's open another terminal. You are using interactive. Okay, so I think, oh, Galileo is not responding right now for me, but hopefully he'll be back soon. Yeah, okay. I cannot log in right now, so I think I'll have to wait. For the login node to wake up. Okay, came back. Okay, so you may try. I don't know if this is edurom, but no, I think it's edurom should be fast enough. Is Galileo working fine for you? Yes.
Could you go back a couple of steps and show us again the models that you load after the login?
Yes, sure. So, can you see the? Well, it's pretty awful, this font actually, but the idea is module load profile global, which is here. And this gives you access to all the packages that we prepared. Okay, and well, then you may load, for example, module load CUDA 9.0. And I'll tell you in a second why I'm asking to do so. Okay, so I showed two things. One is how to load a compiler, and we'll be using our compiler, of course. But right now, we are using just commands from the CUDA toolkit. So actually, NVIDIA SMI comes with the CUDA driver. So it's something that comes with the GPU. When you install the GPU, you install the driver. With the driver also comes NVIDIA SMI. And there is another application which comes with instead with the toolkit, with the CUDA toolkit, which is a set of APIs for developing and using GPUs for scientific computation. And this is called device query. So since it's taking quite some time to log in on the GPU nodes, this is something we'll have to sort out, but we'll do it later. So this is device query, comes from the toolkit, the CUDA toolkit that we install to do actual programming on the GPU. And so, well, you have seen NVIDIA SMI on the login node. Later, we'll try to fix the problem for accessing the GPU nodes. If you do device query, I wanted to show a couple of important numbers that you find there. So as you see, I did it on the login node because it detected two CUDA capable devices and is a K40. And you see that I loaded the CUDA driver version 9, but the thing I want to focus on is this number here. So is the CUDA capabilities. Let's see. This number here. Yes. Yes. Yes, runtime variation depends on the CUDA module that I loaded. Instead, the number that you see, the number that you see here, I may use the pointer, is so-called CUDA compute capabilities. And for this K40 is 3.5. And this is an important information because it tells you the architecture and the set of instructions that your GPU is able to process. So whenever you approach a new system with NVIDIA GPUs, you want to check the compute capabilities of the device. And this device is quite old, so we are using compute capabilities 3.5, which is generally translated into 35. So sometimes you see the dot goes away. And for newer GPUs, for example, for Pascal or for Volta, you have CUDA capabilities which could be, for example, 6.0 or 7.0. So whenever you want to compile a CUDA code, an accelerated code, well, however you may generate it with CUDA, with OpenACC, with other approaches, with OpenMP, with other approaches we'll see later, you should always check and provide to the compiler the type of the version of the CUDA capabilities, compute capabilities that your device has. If, when you are able to run the device query, by the way, by loading the CUDA module, everybody should be able to do device query on the login node. True for everybody? Fine. Because it's needed for the steps that we take later. So you see there are also other things like the size of the global memory and the things that I just told you, right? 15 multiprocessors, 192 CUDA cores, that adds up to 2,880 CUDA cores. Okay. Okay, so let's move on. It's already pretty late, so I try to be as fast as possible. How do you work with a GPU? Well, the first thing to notice, and I will keep telling you this all the day long, is that the memories of the host and of the GPU have different addresses. So you cannot address, I mean, at least for today, unless you use some special tricks, but for today, because that's what actually happens, and we want to stay close as possible to the real architectural structure of the CUDA programming model. So you cannot access memory addresses on the host. So on the node that hosts the device, the GPU, from inside the GPU, and you cannot access addresses from the memory on the GPU as well when you are on the host. So this means that what you need to do when you want to accelerate a code is that somehow you have to move the information that you have on the main memory on the GPU. And so first you need to allocate some space for doing that on the GPU. You now have an address, a memory address on the GPU. Then you transfer the data. Then you execute some code on the GPU, and these codes are generally called kernels. And when this computation is done, you move the results back from the device to the host, and eventually memory is deallocated. Okay? So this is more or less how all the computation with accelerated devices looks like, at least GPU devices looks like. So how can you exploit GPUs? Well, there are mainly two approaches. The simplest is probably just exploiting someone else's work. And CUDA and NVIDIA spent quite a lot of time creating extremely efficient libraries for doing a number of things. And if you are doing scientific computation, I really believe that you may end up using one of these libraries for the task that you have to solve. It's very hard to beat the performance that these libraries provide unless you have very specific task that you want to do. I'm not going through all of them, just the most important one. QBLAS is for linear algebra. I think you know BLAS, basic linear algebra. So this is for doing matrix multiplication and vector matrix, so all the linear algebra operations. Random number generation, and this is something that we will use today actually. Sparse matrices, FFT, and there are also a number of template libraries for accelerated programming. There is also matrix diagonalization and other linear algebra operation, more or less equivalent to LAPAC, provided by Magma and also by Kula. So, okay, I'm not going through all of them. The advantage of using libraries is that, are probably provide the best performance for the problem that you have to face, the problem that you are facing. It's more or less a drop-in replacement of a library that you already have or you're probably already using, like FFTW, for example. And and this is already said. There are a couple of cons, and this is something that you'll see today. So it may require code redesign, and this is the task that you will do in a few minutes. And if the problem that you have to solve is small, you may end up spending more time in moving data back and forth from the GPU than in actually running the kernel that solves, so running the code to the CUDA library that solves a problem. So these are two aspects that we will see in the first hands-on in a few minutes. Let me just complete the picture by telling you that you may generate CUDA accelerated code with a number of approaches, programming models, and you have directive-based models, which are the ones that you see here on top, OpenACC and OpenMP, and these work for C, C++, Fortran. You have explicit CUDA or accelerated programming with CUDA and CUDA Fortran, which can be used for C, C++, and Fortran. There is also OpenCL, that is an open standard, and that is an explicit accelerated code programming model that is, it's kind of losing momentum, but it still can be used for C and C++. I haven't seen any production level implementations for Fortran, and there are frameworks for C++, and there is also possibility to accelerate Python code with PyCUDA. By the way, information for the lecture of tomorrow. How many of you know Python? Well, maybe it's easier to say how many of you don't know Python. Okay, someone. Okay, fine. So I'll tell for the lecture of tomorrow. Okay, so this is the aim of the hands-on that we'll do today. So I'll try to give you the minimal set of information to understand how how the porting of an application to GPUs is done, what are the problems that you have to face, and will accelerate the the problem that I introduced at the very beginning with these two approaches, OpenACC and CUDA. So you can also see from a development point of view the changes that you have to introduce in the code. You can get an idea of how much this increases the load on the programmer to maintain a code ported to GPUs. So I think it's an interesting point. Well, it's also an interesting point to understand how these programming models change the source code, so how you can maintain the code, not only the instruction themselves. And well, okay, so I think it was better not to lose time anymore. So it's 10 to 10. So well, we may start with the hands-on, and then we'll have a break. So maybe we have time to download the code, compile the code, get it running on the GPU, so understand why you are not getting nodes with GPUs when you ask for a job. In the meantime, these examples are very small. Don't worry, you can use the login node. So first thing is downloading the repository with the exercises. Everybody has it? Fine. So there is a folder named CPU, I think. And inside the CPU, there is the code I took from Rosetta code. And all of you know how to compile a C code, or I have to go through that? Okay, fine. So you can just GCC the code on the CPU and run it with time, and maybe write down the time it took. In the meantime, let's try to improve this. Select font. Okay, this is better. Ok. Ma mia connessione è saltata.
C'è qualche opzione per richiedere della REST
Sì,
esattamente.
esattamente. Io ero convinto che la reservation che vi hanno dato esatto, puntasse solo in auto con le GPU. Evidentemente non è così. Sto provando proprio adesso. Guarda, posso farti vedere subito, cioè farei vedere subito l'opzione se riuscissi a fare il login. Purtroppo.
Vuoi provare dal mio? Sono lo vedo io.
Beh, comunque
Guarda, io l'avevo chiamato così.
meno GRS.
Guarda, io l'avevo chiamato così.
Meno GPU ci vuole Kepler. 2 punti, Kepler, 2 punti, 1.
2 punti Kepler.
Sì.
Invece di GPU fai GPU.
No, GPU giusto. GPU 2 punti, Kepler 2 punti, 1. Nel frattempo cerco di fare il login con il DROM che mi ha sbattuto fuori. This is a big problem. dovrebbe essere così, 2.1.
Mi dà anche mi dice che job submission failed, request not configuration is not available. No, ho fatto una richiesta impossibile.
Allora, o te l'ho detto sbagliato, oppure... Allora, io adesso volevo riuscire a connettermi, però sennò qua non va bene.
Purtroppo sulla documentazione c'è ancora la documentazione per PBS. No,
Allora. Perché se c'è un problema troviamo la soluzione. Okay. Okay, so it's dovrebbe essere così. Meno meno GRS, GPU, 2 punti Kepler, 2 punti 4 per prenderne 4. Una dovrebbe essere sufficiente in realtà. È piccolino qua in... Allora, un attimo che facciamo così. Il resto non importa, cioè il resto è specifico per il mio... per la reservation che non sto usando voi, però l'importante è capire se questo comando funziona anche sul... Non funziona, è scritto così. Allora questo... Meno meno GRS uguale GPU 2 punti Kepler 2 punti 4 1. Perché la partition è diversa. Quindi in realtà yes. Okay, you compile the CPU, right? Yes. Fine. I would do something like time apod.out. Oops, there is a... Well, what do you want? It's that one will take some time, but not too much, in the sense that you shouldn't be killed by C groups, and it's a serial one. So you may run on the login node if you want. Why not? Run it also on the compute node. It's better. This is a CPU core, so you can just do what you did yesterday. You already used the compute nodes, right? For doing the other exercises, the hands-on on the MPI and OpenMP, I think. So you can just log in on the compute, schedule a job for the compute node and run it. Is this doesn't sound clear? Okay, so I can go. I assume that this was introduced in the previous lectures, but we can repeat that.
Your recap
Yes.
for the audience is better, I suppose.
Okay, so the only problem is that my connection keeps... Yeah, my connection keeps dropping, so there is no hope to have... I should... Continuate le loro. Adesso, mentre c'è la pausa caffè, ecco, questo è un problema. Mentre siamo al caffè, chiedo info allo user support per vedere se funziona. So, concerning your question, as soon as I have a stable connection, I can show you again, but the idea is that you have to use learn to schedule a job, and you have to. Grazie. Ok. Ok, fantastic.
Bisognerà sicuramente rientrare perché ti cambia rete, cioè è su una rete diversa del node in cui...
Sì, ma sta funzionando molto meglio e quindi so we can check on which slides this was presented, but in any case you have a number of commands for an interactive job. You may use salloc, and this will grant you an allocation on a compute node. You have to specify a number of things. One is the partition, and the partition, I believe, is well, this I have to check with previous user prod. Fine. And there will be a reservation probably too, so -r something that I have to check out. Then t is time that you want to that you are asking for the node, and 1 is telling that you just want one node. Number of tasks per node is the number of MPI processes per node, and that's it. Of course, the reservation is not valid, so you have to remove it. And this command will give yes. Whoa, that's true. This is pretty bad. Sorry, I have to duplicate the screen probably. Okay, so this is the command. The only thing you're missing here is the reservation name. Do you have it from the previous slides? Like what? How you did yesterday to do the exercises on MPI? And that's it?
Partition, job name, error out, and account.
Okay. So, okay, fine. This probably tells me why you are not getting the GPUs. But in any case, this gives you, this is the same thing. You can specify the information that he just listed. So I can make it a little bit bigger, but well, I can just let's so it looks like this. P is the partition, GLL user prod, T is time, N is number of node, and N is number of tasks per node. If you do like this, you are bigger. Yeah. Okay. Sure. Ok. Ctrl più? Proviamo. Yeah, no, it's not bad. I can do it here. So okay. So this gives you an interactive job, and notice that I was on node 165, which is the login node, and I'm still on node 165, but it's not a mistake. If you run srun host name, for example, you see that with srun, the command is actually executed on node 483. So what you should do when you are in an interactive job, like the one I'm showing now, is srun, name of the executable, and all the parameters. In our case, for the thing that you just compiled, would be srun time dot slash, oh sorry, I changed the language, a dot out. And this would be executed, for example, on node 483. Let's try. Yes. CPU. There is something here. Let's see. No, wait. This will, yeah. The problem is there is buffering, so you will not see. That's true. It told me so. So let's stop here. I will check the problems with GPUs, and when we come back, we finish this task. Okay, so let's see.
Però devi darmi da lavorare in remoto. Ce lo devi compilare adesso perché... Sì, perché usa il compilatore di Nvidia, per cui non so... Quindi è... Esatto, no, Makefile. E poi dentro... no, Makefile solo là, il resto Tanto più o meno stiamo 2 minuti e 48 con questa cazzetta.
Ok. S3 Trento GPU. Posso chiederti una cortesia, se non vuoi andare al bar? Prova ad aggiungere reservation, meno reservation. Certo, certo. Uguale, credo ci sia. S, trattino basso, tra, TRA, underscore, sempre, Trento GPU. Tutto attaccato, tutto minuscolo. Questo is a big problem perché stai facendo il login con uno degli account. Esatto. Esatto, doveva essere attivo per oggi. Cioè, è stato fatto avendo l'accesso con gli account A30.
H08-64. E questo qui è il file che sta girando adesso.
Sì, mi sembra giusto.
Aspetta,
Reservation? Quello deve restare, sì.
ok, la reservation.
La reservation è S, underscore trata into GPU, job name, whatever. E se...
Account e pay 30 dovrebbe essere.
No,
No.
l'account dovrebbe essere uno degli account che viene...
Scusate, ma invece che farlo su base individuale,
Sì, sì,
dopo
sì,
la pausa, perché non lo ricapitoliamo e ci fa
sicuramente.
vedere e magari poi noi
Almeno prima lo
Più che altro volevo essere sicuro che funzionasse, perché non vorrei che fosse il mio...
gira, è quello il problema.
No, è 3018, che devo controllare se è l'account che è abilitato.
Funzionali non ci piaceva girare con A08.
Quelli?
Con A08-64 non gira. Non girava gli altri giorni. Abbiamo dovuto mettere 30-18 per farlo girare. Se vuoi lo faccio girare col nome.
No, va bene, va bene, va bene. Però tu stai facendo il login con A08 tra 60 qualcosa, quindi deve funzionare. No, no. L'errore che ti dà è?
Adesso lì ho messo A08-64.
No, no, l'account è, no, no, l'account è giusto, trainer. No, 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 è il login name che...
L'errore che mi fa è batch job submission failed, requested reservation is invalid. Si possono listare le
Yes.
reservation?
Prova a mettere, anziché GPU prod, cioè, scusami, anziché prod, GPU prod.
No, no, appena
Sì,
realizzato.
sì, sì, esatto.
Ho schiacciato in realtà.
Io ero convinto che...
Prova a togliere la reservation.
No, 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 adesso non ci vuole.
Va la
Perché mi sta
con i cavi.
la reservation.
Stai facendo
Prova, ma...
Intanto solo un attimo torna in video.
gli incubi dell'impianto elettrico.
Questo è strano.
Non mi ricordo dove sparavo fuori, dovrei sparare fuori. Yeah.
Ha funzionato, quindi strano, però non ci vuole la reservation.
Non ho fatto fare lo screen, non so se era.
Io sono. Cioè,
Vabbè, vabbè, comunque...
io. No. Io non ci
Ottimo.
Ti passo il file.
Sì, mi faresti un grosso favore, così lo faccio vedere. Strano, la reservation dovrebbe essere attiva e dovrebbe garantire la possibilità di... Attiva dalle ore 10. Quindi sono ben... Oddio, le ore 10 sono adesso, però... Anzi no, no, scusa, dalle 8 alle 18, quindi... P.bomb Okay, sorry. So just a few words before we go on with hands-on, and I describe briefly the hands-on. One of your colleagues was kind enough to send me the job file that allows you to get access to the compute nodes with the GPUs. So, very short recap on scheduling and accessing compute nodes on a cluster. You cannot SSH. Resources are provided by a software which is called scheduler that gives you a compute, one or more compute nodes when they are available. And so to ask for resources to the scheduler, you have two approaches. You can do interactive jobs, or you can do batch scheduling, where you create a script, a bash script. Bash script is okay for everybody? Someone uncomfortable with bash scripts? Okay, fine. So you create a bash script that will be executed on the requested resources when the scheduler decides so. This is how the script looks like. You see two parts. Top part is the details on the resources that you want. The second part are the commands that you want to run. Let's briefly recap on the first part. I'm not going towards all the options because it would be super boring, but you do see that something is pretty obvious, like the number of nodes that you want equal 1. There is another command, so we are asking for 1 node. There is another command that is what we need to specify the request of a node with k80s. K is short for Kepler. So the command that you see here, do you actually see it, or is too small? It's still too small. Let's Nimbus like this. Perfect, fantastic. So it's third line. This is what tells the scheduler that we want Kepler GPUs, and we are asking for 4 Keplers. We may ask just for 1 Kepler. It's actually what we should do, since we are doing always jobs which exploit 1 GPU at a time. Output and error are the files where standard output and standard error will be written. Account, you should already have it. Okay? That's what you specify the account that you already have. Partition. This is another difference with respect to what you did in the previous days. You see that we are using a partition which is named GPU prod in this case. So remember to change it in the scripts that you have, if you already have some. And job name can be whatever you want. Next, module load profile global. We saw this morning. Just provides you with all the modules that we have. Module load CUDA is something that you need to do in order to have device query. Just put it there, it's useful for today. srun, this is the most important command. srun will run this command according to the information that you provided above. So if you ask for many tasks, for example, yesterday when you were doing MPI, you probably specified something more in this part here, like something like n tasks per node. Okay, so this information is translated into the execution of multiple processes by the srun command. I hope I'm telling you something that you already heard yesterday with the lesson of my colleague Massimiliano. If this is not so clear, maybe we can discuss it later and we focus on GPU code right now. So there is one last thing that we may add to this batch script, so it's complete, and this batch minus minus n tasks per node equal 1. Let me check if that's correct, spells right. N tasks per node equal 1. Yes, so I just copy paste it from here, so I'm sure the spelling is correct. This guarantees that we will be using a single process on a single node with a single GPU. Well, that's it. Okay?
Maybe it's better to remove the job name, or we have all the job name equal.
Yeah, feel free to. Funny name here. Okay, now one last point. Since running the jobs like this is very tedious and takes some time, we agreed to proceed like this. You develop on the login node. On the login node you have a GPU, you can compile, you can test. When you're ready, or you believe you're ready, you can check the results also on the compute node. Okay, so you are feel free to run the executable that you produce on the login node. It will work because there are GPUs also on the login node, and these GPUs have the same compute capabilities of the compute node. They are named different. It's K40, the other one is K80, but the only difference is that one, well, more or less, the only difference is that one has a single chip, while K80s have two chips. Do you remember the picture I showed before? And indeed, on the compute nodes there are two K80s, but if you remember here, oops, here I had Kepler 4. Why? Because each K80 has two chips, and these are seen as 4 GPUs. So if you submit it like this and you run srun device query, you will see a list of 4 K80s. Is that clear? 2 devices, 2 hardware, 2 pieces of iron. Okay? Each one has, yeah, that's the problem with duplicated one. Each one has 2 chips. That's 4, right? Feel free to check it with the command like this. So I go back to what you should use. Now, can I close this page? I can put it on the page of the course, of the lessons of today, if you want. I want to briefly introduce the next first hands-on, which shouldn't take long. like I would suggest we close it in 20 minutes or so. So I leave it here, and someone may, yep, so many things open. So let me do SHPC, voila. In the repository that you see here, I can make it bigger, voila. This is the URL that I gave you this morning. So you find a folder that is called lib. And the first thing I ask you to do is start from the CPU version that you already compiled. You managed to compile it, right? You managed to run it with time. How long it took? More or less. Order of magnitude? On the CPU, on the single CPU. Yeah, that's the right order of magnitude. So, next step is let's start using the GPU with the library. I told you, one approach is using the library. Let's see what we can get from using a library to generate the random numbers. This introduces, as you will see, another problem. So we cannot use the code as it is and just drop the library because it would be too slow. If we ask for one number to the GPU, sorry, if you ask for one number, if you ask the GPU to produce one random number each time, you'll see that the code becomes extremely slow. Instead, what you should do is create a buffer, fill it with random numbers, and then use it. I'm already providing you in this folder a file which is called curand. Can you see it? curand.c, where I already put all the boilerplate code, something that I don't want you to write. So the only thing you want to use is this function, curand uniform on host, where you specify the number of random numbers that you want. Okay, can be one, can be whatever you want, and you have a pointer of type fp, which is double, where this number will be placed. What about the level of C in the audience? And if I'm asking to create a buffer with a pointer, doubles, is too complicated? Someone's saying too complicated. Okay, so you are Fortran developers? Okay, so you would do an allocatable, right? We can work out also the version in Fortran if you want. In the meantime, you can maybe just look at the solution and okay, so your task is get main.c from the CPU version and change it to exploit curand uniform on host. Okay, where n numbers and uniformly distributed random numbers will be generated and put in FP host data, and this function, obviously, but maybe not so obviously, so let me just show it. This function replaces this one. Rand is what you use, well, actually all this line. This line is what you use to generate a random number. Okay? So you have to do a couple of things, of course. Here you're generating one number every time you call uniform. you will have to change a little bit uniform and try to use the buffer. For those who are not familiar with C, we'll comment the solution. You can just look into the main.c in the solution, and we'll comment the solution in a few minutes. And if you have questions, of course, I'm here, and feel free to ask me. I will be around and helping you. Come? Tu vorresti un header per fare un include fatto bene? Sì, sarebbe giusto. Io le ho messe nel main.c, sì. Sorry, maybe I should speak. So he is complaining, and he is correct, because there isn't any header describing the prototype of the C functions. But so I mean, we are here just to focus on the on how to program with GPUs. So feel free to just put in what you need in main.c to make it compile and run file, and maybe later we can improve the style of the code. One important thing that is missing here, I may probably add it. You need to load CUDA. So I will add right now the modules that you need. questa... No, non so se quella là è la mia o questa qua, chi lo sa. Non so se lo sta vedendo con me. Poco importa. No, secondo me è quella che ho preso da sotto. Vabbè, sprechiamo.
Scusa, devi utilizzare solamente lo uniform o
Ok, no, there is, sorry, I forgot an important thing. There are two other functions that are important sorry, my fault. In Courant.c there are two other functions that were the one that I wanted to forget about, but I have to tell you. And those are Courant init and Courant finalize. Just put them before and after calling a Courant uniform on host. Anywhere you want. Just call it once, initialize and finalize, and put them wherever you want before the first call to CUDA uniform on host, and the finalization at the end, before return. Scusate, voi siete i fortranisti. Ah, tu Python, ok.
però nel senso che preferisco, nessuno l'ho mai visto in C poche volte, per cui
Ok, allora in realtà si potrebbe anche... Allora questa parte qua è piuttosto rilevante per tutto quello che si fa dopo. Io faccio una presentazione, se riesco, su CUDA Fortran. In realtà si potrebbe anche riscrivere questo main.c in Fortran e poi almeno la parte di OpenACC si può fare in Fortran. Quindi magari provo a buttare giù due righe. Cioè se tu sei abbastanza pratico di Fortran, magari puoi buttare anche giù tu il main.c in Fortran e poi almeno sulla parte di OpenACC lo giriamo col Fortran. È abbastanza, cioè è tutto uguale, l'unica cosa...
cioè tranquillo, non devo creare problemi.
No, che problema, siamo qua apposta. Cioè,
Si trovano in un certo modo, comunque
su Rosetta Code secondo me c'è già almeno un pezzettino di Fortran e da lì si può partire per non riscrivere tutta la parte noiosa. No.
Lo trovo proprio...
Sì, prova a cercarlo su Google. Infatti devo cambiare. Sì, è proprio quello. E adesso bisogna cercare Circles Area. Mi sa che devi cercarlo con... sì.
può essere...
Circles... L'ho trovato. C'è il link. Total, yes, eccolo lì. Sì. Eccolo lì. Quelli sono i punti. E Rosetta Code è carino perché c'ha tutti i linguaggi che ti puoi sognare. E quindi se lo vuoi... Purtroppo temo che la soluzione Monte Carlo in Python c'è. Quella è la soluzione in C che ho copiato spudoratamente.
Diciamo che uso Python e Java, però Java ha un utilizzo abbastanza rudimentale della cosa.
Ok, in Fortran dovrebbe esserci No, cazzo, Fortran non c'è. Mi ho fregato. No, non c'è Fortran. Posso provare a buttarlo giù in Fortran. Intanto che aspetto ancora qualche minuto. No, Fortran non c'è maledizione. Però è abbastanza facile, adesso provo a buttarlo giù in Fortran. In Python non ho nessun riferimento, onestamente. Cioè, you're on your own. Prova pure, ma non ho... Cioè, conosco Python, ma Python e GPU non ho mai provato. Quindi...
Invece, Java si riesce a mandare su GPU.
Ma alla fine, tutto quello che puoi fare tutto quello che puoi fare un binding a C funziona, grosso modo. Allora, Fortran puoi girarlo sia col CUDA Fortran che facendo dei gran binding a funzione di C. Cioè fai un wrapper e sposti i dati, Fortran te lo consente. Python anche, però Python c'ha già un set di, insomma, di pacchetti che si occupano di questo. Java immagino abbia anche lui non conosco affatto Java, onestamente. Quindi immagino che ci abbia delle interfacce per parlare col C.
Sì. Ok, era solo giusto una curiosità.
Java è fuori dalla mia...
Vabbè, ma adesso ci mettiamo qua, abbiamo 3 teste, 3.
Beh, insomma, comunque se
Vediamo di fare
avete...
programmi in Fortran.
Va buono, dai, sì, il programma in Fortran viene utile anche a me. Ma no, potresti anche farlo come vettore, cioè alla fine quelli sono... Allora, quelli lì sono x, y e raggio. X, y e raggio che tu ti cerchi. E quindi, volendo, si può anche allocare con un array bidimensionale. L'unica cosa è mettere l'ordine giusto degli indici, ma se lo alloghi con un array bidimensionale stai a posto. E poi il resto è abbastanza chiaro, cioè dovrebbe essere abbastanza semplice. Grazie a voi, se mi fate il Fortran io poi lo riciclo.
Rimanga appeso, non fa neanche un ciclo uguale. Oppure la sostituzione dovrebbe essere abbastanza...
Prima di dare un'occhiata. Adesso lo ripeto anche, tra l'altro.
Allora,
Ok, il sorgente è questo.
sì, io ho fatto un include di curand C e l'ho tolto la
Ok.
configurazione come se fosse tutto
Ok.
Poi qua nel main c'è l'init e alla fine c'è il finalize.
Perfetto.
Dentro lo uniform
Sì.
una fatta bruttissima.
Sì,
Ho fatto
sì,
un
sì.
array e poi current uniform host, dimensione 1, il puntatore è 01.
Ok, secondo me questo potrebbe metterci qualche anno.
Ok, addirittura.
Sì. Prova a fare un numero di cicli bassissimo.
Ah, quindi tu dici eliminiamo il for, quindi lo modifichiamo proprio per eliminare...
No,
scusa,
cioè, scusami.
il while.
Sì, cioè anziché dirgli questo size to try, mettici una roba tipo 4, cioè una roba scandalosamente bassa.
Scusa,
Lì,
qui?
sì. Invece quello è un intero, no? Sono vabbè, uno spostato di 16. Questo qui è tipo... Ok, fantastico.
Ok, va bene.
Ok, hai visto? Cioè questo qua... Questo è proprio quello che volevo
Sì,
che non riusciste...
perché devi tutte le volte creare memoria sul... un elemento di memoria, un'istruzione sul
Ok,
CPU,
perfetto.
e poi fare il trasferimento dalla GPU alla CPU, quello per un sacco
Ok,
di tempo.
esatto. Allora, io ti proporrei di guardare la soluzione, ok? E puoi anche copiare il main così com'è e provare a girare quello, compilare quello e girare quello con un time, sempre sul login oppure sul calcolo, sul calcolo, se vuoi vedere un pochino più e vedere quanto cambia. Adesso tra un po' poi... Cioè, perché questo era proprio il punto che volevo sollevare con questo esercizio, quindi fa molto piacere che sia...
Ok, quindi era voluto che andasse così lento.
Sì, 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 sì.
Semplicemente
Se guardi la soluzione c'è scritto come farlo andare un po' più veloce.
la soluzione allocchi in blocco sul device.
La soluzione, no, nella soluzione alloco un array più lungo e carico più numeri alla volta.
Però c'è un gioco,
Sì,
bisogna usare spazio dopo lo script, quello che le hanno passato.
sì, basta, messo un fade, register, node, configuration, ok,
Quello ho
guarda.
sbagliato qua in questo.
Allora, dunque, end task per node intanto mettiamola 1, perché questo è seriale. Questo deve essere GPU prod.
Questo?
Prima di prod ci vuole GPU.
Ok, quindi
Dopo il dopo, no. ASR underscore
sì,
GPU, togli l'altro underscore.
Ah, ok.
Ok, così. Questo dovrebbe andare. Intel MPI, boh, vabbè, chi se ne frega, lascialo lì, non serve, ma... Ok. Questo è quello... Ah no, questo è già quello con CUDA?
Sì,
Ok, fantastico.
va bene. Cioè, nel senso, è tipo, mi ha compilato.
Sì, dovrebbe andare. C'è Intel MPI che non serve a niente, ma va benissimo, vediamo cosa dice.
Per ora
SQ? No, SQW, scusami. In italiano SQW. Meno U, spazio meno U, e il tuo username, che è A08-72. 72, hai messo una O, mi sa, al posto di uno 0. Is running. Credo. Come l'hai chiamato?
Bagnerol qualcosa. Underscore Bagnerol.
Ce n'hai due, uno pending, uno running. Il più recente mi sembra che sia pending. Mi fai vedere il job? E scr.sh. C'è scritto reservation da qualche parte qua?
Non credo. Questi sono commenti.
Partition, no, non vedo.
Reservation.
No, ma allora forse sta girando, non lo so. Vediamo un po'. Quello ti dice quante GPU stai prendendo.
Le faccio schifo?
Sì, vediamo un po' che sta. Pending. Beh, però no. Name Nvidia. Nvidia, l'hai chiamato Nvidia qualcosa, vero? Allora quello lì è in pending. Perché è in pending? Forse perché non ce ne sono abbastanza. L'hai chiamato name. Ah no, job MPI si chiama.
Magari ero scritto.
Quindi non lo vedo nell'elenco di quelli che hai girato.
Quindi non l'ho andato.
Name bash. Name. Sì. Prova a cancellare quello lì intanto, va. Non so che cosa sia. S-cancel. Ah, perché voi non sapete niente di Slurm. Cioè, non vi ha fatto vedere i comandi.
Guardi, io non c'ero neanche in tutte le sedute, quindi
Vediamoci pure del tu. Comunque,
quella di ieri, cioè, possiamo anche toglierla perché non è che si sia capito moltissimo. Quella dei primi 2 giorni non so, non mi ricordo se si è detto. Comunque cosa deve essere?
ok, S-cancel.
Esca.
No, S come S. Te lo dico in italiano. S tutto attaccato a un comando, cancel. E poi i numerini che ci sono lì, cioè U4, 1, 3, quello lì. Ah, ma sai cosa? No, l'ho capito adesso. Voi state condividendo gli account.
Sì.
Ecco perché, allora questo non sei tu, sì, sei qualcun altro che sta girando.
Sarà, sì.
Sì, ok.
Però sono sempre questi.
Bisognerebbe capire chi è quello con la reservation che sta in pending. Comunque, login node va bene, eh? Cioè prova a girare sul login node.
Puoi mettermi come per favore per essere
certo, punto, allora, tu hai generato un eseguibile che si chiama punto barra a.out.
No, si chiama E1.
È vero, si chiama E1, però puoi fare punto barra E1.
Proprio semplicemente così.
Sì. Errore segmento. Ok, vabbè, questo va bene, perfetto. Adesso lo dico ancora un altro attimo a tutti. Sorry, I repeat it once more. When you're testing the files that you compiled, feel free to test them on the login node. So there isn't anything that is going to crash the system or you won't be killed by the administrators of the system. So killed in the sense of process killed, not you. So feel free to compile and run on the login node with dot slash and the name of the executable that you produced. And later on, if you want to really benchmark how you did, okay, you can submit a batch job as I showed you. I understood that even sorry, also the commands of Slurm are not so clear to use, so maybe maybe I introduce them well, but maybe let's finish this part and then before moving to the next hands-on I will introduce briefly the commands of Slurm again. So it's more important for the rest of the hands-on. I would like to stop this hands-on in like 5 minutes, so we have an hour more or less to start with the new topic. So I give you a few more minutes to go on working on this. It's the least important task for today, so if you didn't manage to get something working, no worries. We'll discuss the results and move to the next topic, which is much more interesting. Allora. Potremmo fare una paginetta su Slurm. Questo bisognerebbe adesso. Vabbè. Questo scusami, questo viene registrato? Okay, slide. So maybe can you switch off for a second while I can just okay, fantastic. I don't have many secrets, but my emails. Vediamo un po' cosa c'è su Slurm. Adesso ricomincio. Discuto brevemente la soluzione. Potrei chiedere. It's still active. Okay, so well, yeah, during this hands-on session, where I'm interacting with the students, so maybe it's not very interesting.
If you prefer, you can switch off the...
I can switch off the microphone.
Yes, yes.
Yes, fine. Yeah, I mean, no secrets again, but mute. Is audio working? Can you? Okay, fine. Okay, so I think it's time to move on. So the aim of this exercise was actually to show one of the cons in the slide discussing how to exploit GPUs with libraries. So I borrowed this approach from one of the students here in the room, so one of your colleagues, and he did correct, like we have to allocate, we have to fill some memory with random numbers, so he just replaced uniform and the code that you see above there with an array of dimension 1, then it fills it with current and return. Now if you do like this, the code will take forever. Like, I mean, I don't know how long did it take? You have an idea how long did it take to do just a few iterations? Like, you killed it. Okay, fine. So, but I may think more or less it was doing like well, yes, I think it took seconds for doing like 4 iterations. Why you do millions on this group? And that's the point of this and so on. It's very often it happens that you have to change a little bit the structure of your algorithm to exploit the power of the GPU. And in this case, the solution is here. You do find it in solution main.c, and the solution to gain something, but actually if you try to compile and run the solution, you see that you don't gain much. We can discuss this maybe later. But the solution is to allocate a buffer where you fill the random numbers. You need random numbers for the x and for the y, so I'm making it 2 times trials that you want to make, and then you fill it here. Or maybe I can use the mouse so everybody will see also in the streaming. And then and then you use it like this. So as you see, I had to change a little bit the structure of the code to explore the GPU. If you feel free to compile and run this version and the original one, you'll see that there is a speed up, but it's a modest one. Why? Well, that's obvious, because the computation, the real compute intensive part, is still on the CPU. So our task now is to move to the next topic. So how do we move the computation on the GPU? And to do this,
Sorry.
yes,
So only one
of
question
course,
on the solution. Because
as many questions as you want.
online in the if inside of the while, when you evaluate again a new random number,
Yes,
there is a real lock.
yes.
And if I don't put that real lock, I have a segmentation fault, and it's not clear for me why without a real lock, because I thought I was rewriting on the buffer that I created with the calloc function.
Well, it might be a bit stupid. Well, let's see. To try changes, yes. So, well, the fact is that ntries, I think you're correct, ntries is not changing. So it could be made much better. Yeah, it's a mistake probably. So it tries.
I don't do the real lock, I have a segmentation fault.
Yes,
But
but because you are not using. Exactly, and tries should be reset. Yeah, that's a mistake. Actually, thank you for noticing that. We can correct it. Yes.
No, the I round must be resetted.
Sorry, only one.
It's a little stupid, I think. It's not a mistake, but it's a little stupid. So you want to do, so you're increasing the number of trials that you want to make. So,
È un numero e sto accedendo al vettore con i rand e quindi e quello è resettato. Quindi non
Erand is reset. I mean, I think it's not the best implementation that you may have. So Erand is reset. You are increasing the number of trials you are doing, right? So you are increasing the number of trials you are doing. So you have to reallocate to make more trials, okay?
okay.
And
Sì.
but it's not the best implementation, I agree.
No, I see that.
But
I noticed that
yes, that's why there is no, the 2 here is not there anymore. Yeah, it can be made better. I think I will make it better.
no, but now it's clear why I'm doing the segmentation for. It was an algorithmic issue.
Let's move on to the interesting part. Here it is. Okay. So in the next hour, I'll try to introduce how to move the computation on the GPU with the CUDA programming language. So it's flickering a bit. I hope it works on the register. I think I already introduced this, but I want to repeat. These 2 words will be, you'll see them pretty often in the next slide. So whenever you see host in the next slides, it means the CPU and its memory. Whenever you see device, it refers to the GPU and its memory. As I told you, these are different entities, and computation and memory computation takes place on the CPU, working on the memory of the CPU. You cannot directly access the memory on the CPU. You need a set of APIs that I will introduce with the next slides. So, how do you write CUDA? You have 2 options, at least what we are looking today is for this programming language. For C and C++, you write with an extended version of these languages, which is called CUDA and is provided by NVIDIA. So right now, I'm telling you something that is specific to NVIDIA GPUs. There are some attempts to do source-to-source compiling to have CUDA code running on other GPUs, but at the end of the day, what I'm mainly teaching you today works for NVIDIA GPUs. If you have Fortran codes, you may write CUDA in a Fortran-like way, so with a syntax that really resembles the Fortran syntax, with CUDA Fortran. Okay. If there's time, I'll try to discuss it later. Now let me introduce the compilers. We will be compiling CUDA code with NVCC, and NVCC is something that you find in the CUDA toolkit, and the CUDA toolkit is the thing that you have when you do module load CUDA /9.0, for example, in the examples that I showed this morning. For the CUDA Fortran version, instead, you can use the PGI compilers. That's what implements all of the standard, while EBN compilers implement it partially. And in this case, you really only have this option for CUDA Fortran. This is how the compile looks like. Someone tell me what's this 35? Right. Okay. Don't forget this, otherwise you may have fancy errors or very mysterious problem in the code. Okay, let's start. We'll start with the hello world of CUDA, and I will be considering only CUDA C right now. I have a presentation also for CUDA Fortran. I hope we have time to show it. Okay, this should be easy enough for everybody in the room. Let's add some CUDA. So there are two additions here. One is this one and one is this one. Let's consider the first one. First one is the declaration of a function that will run on the device. How do you understand that the function will run on the device? Global. Global actually means that we are defining a function that will run on the device, and this function can be called from the host. Okay? Second difference is this one. This looks like a function call, but there is this funny syntax that we'll discuss in the next hour. This is how from the host, remember the definition, so this is how from a code running on the CPU, we schedule on the GPU the execution of kernel. And kernel can be scheduled on the GPU because of this attribute. Okay? The rest of this code, this part here,
So we are calling the function defined before. That
say it again, sorry.
in the main, that kernel is simply a call to the function defined.
Yes. 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 I'll tell you more about this in, well, quite some time, but I will come back to that. Okay, so this is pretty boring, just does nothing. Oh no, well, actually the answer is right here. I forgot, I put it in here. As I said, this will trigger the execution of the kernel on the GPU and return immediately. So, yes, so this means that, well, this function does nothing, but if you had a long computation here, you may as well do something here on the GPU.
Should the program exit then?
Well?
Will the program exit or there is a...
No, there is an implicit synchronization at the end. Okay, let's do something interesting. Again, I hope this level of C is okay for everybody. What I'm doing here is creating a kernel to add a couple of numbers and to store the result in C. Okay? Nothing more than that. But in order to do so, these numbers have to be, these are pointers actually. These pointers needs to point to some data on the GPU. How do we do so? How do we do that? Well, there is a portion of the memory of the GPU that can be accessed both from the host and from kernels on the GPU. This is the global memory, okay? So we'll discuss this later. And how do we reach the global memory from the host? We have a set of instructions that are provided by CUDA. These instructions are CUDA malloc, CUDA memcpi, and CUDA free. Okay? What these instructions do should be fairly evident to all of you, apart from this funny syntax that is probably not so clear for those not familiar with C. But, well, what we are doing here is allocating an int, so something with the size of an int, on the GPU, on the global memory of the GPU. And we are doing it for A, B, and C. And we are storing their address in dev A, dev B, dev C. Then we are setting a value for A and B. But this value now is on the host. The value on the GPU has not changed. So what we have to do is synchronizing this data. So these two calls, what do they do? Well, it should be pretty even. They copy the memory, destination, source, size, description, memcpi, host to device. Clear for everybody? Okay, fine, not bad. Then we run our function with this funny syntax that will call the function and do this. And this works because we are accessing the value of B, accessing the value of A, and storing the sum, this sum, in the position pointed by C. Once this is done, what happened? Well, we need to copy back the result because there is no way from a code on the host, for example, print, if we want to print the sum, to access the memory of the GPU. Next step is copy back. So you see that the only difference here is CUDA memcpi, memcpi, cpy, device to host. Okay? And then eventually we free the memory on the GPU. As I told you before, now we are calling the function add. Always remember to give the address of some memory on the GPU. If you call this with A, B, and C, page fault. Okay, so the address is not mapped. Okay, fine, we can sum two numbers also on the CPU, it's not a big deal. How do we sum? Is that clear for everybody? Okay, fine. How do we sum more than two numbers? Okay, let's start with something which is specific to CUDA. In CUDA, we have a thing that is called block. When you are in a kernel, in a CUDA kernel, you do have this variable filled with the right value for you by the CUDA runtime. You can set the values that block edx will have at call time. Let me first check what happened on the GPU. So on the GPU, when you run the kernel, the GPU creates a number of blocks with their index. Block is actually a 3D thing, so it also has Y and Z, but we'll totally forget about that for today. It's a generalization, but something not useful for our introduction today. So what happened to blocks? Blocks, and this is where I wanted to draw something, but I think I moved it, are dispatched, are given to the streaming multiprocessor. And the streaming multiprocessor will execute a thing like this. one will execute, for example, block 0. Another one will be executing block 1, where this variable here has value 1. This one has value 0. And so on, up to the number of blocks that you have. You cannot control it. And if you look carefully, 0, 1, 2, 3, 4, 5, sorry, 7. Is that a mistake? No, it isn't a mistake. The order of execution will be decided by the scheduler. You don't have access to that. And this means that this instruction here, each of these must be independent from each other, right? Okay, so next question is how we have to change this for adding many numbers. I already introduced this. How do we set the number of blocks that we have? Like this. You see the funny command, this funny brackets that you have here. I've been setting, I don't know. So, by setting n here, we set the number of blocks that the GPU will create for us to execute this code. This is extremely important. Is it clear for everybody? Yes.
So if I let 1, comma 1, I can get a pointer in the definition, and it's for a value,
Yes.
single or double. While if I put n, it's for an array.
Yes. Let's forget about this for a second. I'll be moving to the second number in a few slides. But you are correct. You may as well put n equal 1 here, and this will continue to work. Okay? And this will add one number, as in the example that I was showing before. But if you want to sum more numbers, you may use blocks. And with blocks, you set the number of the number of numbers, the dimension of the array that you want to sum here, and it gets summed in each block, element by element. Okay?
The size of the block is limited by the architecture of the GPU or not? I mean, there you use 512. But if the number would be, for example, 3 order of magnitude greater, how would it go?
There are some limitation of the number of blocks, but actually the real limitation is on the next thing that I will introduce. So that's, I would prefer to answer your question after, when we also check these numbers with the commands that I showed today, device query. Okay, new concept. Each block can run several threads. Answering a little bit your question, if you check device query, I believe that for the K80s is up to this number. So, let's forget about blocks for a moment and let's repeat the, yes?
A block refers to a CPU on the, to a processor on the GPU.
Honestly, I think the best thing, at least for the moment, is forgetting about mapping of these entities that I'm introducing and the hardware architecture. Yes, they are executed by streaming multiprocessors, and the architecture is of course tightly linked to the concept I'm introducing. But for the moment, let's think that a block is a piece of code that is executed out of order together with other pieces of code by a scheduler that will dispatch this block in the best way he believes this can be done. At least it makes things more easier for the moment. Okay, so new concept, as I told you, each block can run several threads. So let's repeat the exercise we did before. Instead, but instead of using blocks, let's use threads. How are the things changing? Well, we just have to replace block index with thread index. Not a big deal. How does the initial code change? Well, you see, it's almost the same. I changed this as I told you, but I also changed the second number here. So what are we doing here? We are running with one block and n threads. So at this stage, the meaning of this syntax should be clear, I hope. Okay? First one sets the number of block. Second one sets the number of thread. And this code performs exactly the same thing as the one that I introduced earlier with blocks. Okay, so let's try to use both of them. How do we do? Why should we use both of them? Well, because as I told you, we don't have many threads. We just have up to 1024, I think. So let's use both threads and blocks. All our computations here are independent, so we don't care if a thread of a block is doing something, is summing one element, and another thread of another block is something. All the elements are independent. We don't care. How can we do that? Well, as I told you, each block can run several threads. Of course, we don't want to waste them. We want each thread of the block to work on different elements. And we want the threads of each block to work on different elements. How do we achieve this? It's fairly simple, I think. We have the thread index, we have the block index. The only thing that we are missing is the dimension, which is the number of threads in each block. This will be the same for all the blocks that we are asking for. So the number that we put here, threads per block, will be the same for all blocks. And it's stored in the variable block dimension.x. Okay? So these are the three, at least for today, these are the three variables that you need to deal with when you're writing an application in CUDA. How do we get each thread to work on a different element? Well, we just need to add to the index given by each thread the block in ID index multiplied by the block dimension. Is that clear? That's when probably a board would be useful. If this is clear, I can move on. If it's not clear, I can draw something on the laptop and make it easier to understand.
Like a multiply, this dimension of block E and the number of blocks is the number of all.
Yes. So yes, yes, you can see it also like that. Yes, but you can also see in one dimension, right? So you will be the first block. First block has index 0. That's by definition. First block has index 0. First thread has index 0. So thread index 0 here will be executed by block index 0, multiplying block dimension 5, 1, 2. right? So 0 added to 0 times 512 gives 0. So the first thread in the first block will sum the first element. Let's move to the next thread in the first block. This is 1, this is still 0, and this is still 512. So the second thread in the first block will sum the second element, which is element with the index 1. Sorry for the Fortran guys who are used to variables starting with 1. But don't worry, in CUDA Fortran, these start from 1. So, just for you. So let's move to the second block. In the second block, we will have thread 0 as well. But the block index will be 1 in the second block, right? This starts from 0. So this block index will be 1. And we will be multiplying block dimension, which is 512. So with the first thread of the second block, we will be adding the element 512 of these arrays and putting it in the element 512 of this array. Yes?
Is this the same argument of transforming a matrix into an array?
Yes, it's a row measure ordering a scan.
Yeah. Okay.
Sorry, I have a question.
There should be many questions here.
To those numbers, 2048 and 512 are arbitrary?
No,
Depend on
no.
the device.
No, you can put. So as I told you, this number is limited by the device specification, and device query should tell you this. We will go back and check the results in a few minutes. Well, I fear after lunch, but there is another very important point, and the number of blocks is large enough. And if it's not large enough, you can use the other dimensions. And it also depends on the architecture. And you can get these numbers from device query. But the real question here is, what happens if I change n? Because I told you that in the arrays, in the code that they get executed on GPU, sorry, these numbers will go, this one from 1 to 512, and this block dimension will go from 1 to the number of blocks divided by the threads per block. So you always have to be careful to avoid going outside the boundary of an allocated region, or forgetting some elements in the computation that you're doing. These numbers are fine, because if you do the if you look at the remainder of this division, it's fine, 0. But this is something that you should be careful when doing GPU programming.
Sorry.
Yes.
Just for be clear of the syntax. The first number, so it's the block dimension. The second number, the thread dimension.
Exactly.
Okay, thank you.
If you, I think I should put this online, but I will do immediately after this presentation, so you can look at it again while doing the hands-on. But yes, if you remember, this one was the number of blocks, and this one was the number of threads. But we were introducing the concepts. Now you may ask, why? We already had blocks. We don't have the limitation of 1024 threads. So why using threads? Well, the reason is here. I told you that you cannot control how the blocks are dispatched, but you have a way to synchronize instead threads and to make a communication between threads. I hope that all of you in this room know the dot product. Okay, so we'll be doing this very complicated task. What time is it? I don't have the mirror. I have the
10 minutes to 12.
So we still have enough. 40. Oh, fantastic. Okay, so we will be doing this task, and you probably understand. 30 minutes.
It is almost 12. I read.
Okay, no, I hope it's enough. So you immediately see that we need to communicate here, because we were adding numbers before. We have to multiply the elements here, but at a certain point, this number had to be added. So we need a way to add these numbers. This is called a reduction, probably, you know this. And this is why we need to introduce threads. Let's go back to device memory. I already introduced the global memory, where you can put the data from the host and move it on the memory of the device. There is another set of another space in memory which hosts local variables like this one that are declared inside the kernel. So if you declare this, for example, this integer in a CUDA kernel, this is private to the thread. So no other thread can access it. And you can use it to do your computation, and it's extremely fast. So if you are doing a lot of computation on the GPU with data that you previously stored using a CUDA malloc, you may think of storing it in the local memory of the thread to make the computation much faster. It's a sort of cache handled by the user with this allocation. And that's indeed what we do. Let's use one thread to compute the product and store it locally. Temp is private to each thread, so this is fine. There is no there are no data races here, but we have to finally sum temp in a way and put it back to C. So how do we do that? Final concept for this morning, I think. Shared memory. Shared memory is the third and last type of memory that I introduced this morning. Also, this one is extremely fast because it's again a sort of user-managed cache that you can allocate, and you declare it with shared. But it's shared by all threads in a block, and only by all threads in a block. It means that threads from other block cannot see it. Okay? So this is how it looks like. How to allocate global memory, we saw it this morning. No, well, an hour ago probably. So with CUDA malloc, this is the same as in C, and it's a local variable to this thread. And this is how you set and you allocate shared memory in a CUDA kernel. And this is available to all threads in a block. You see, they all have the same color. And that's how we finally can create our dot product with threads, right? So what we do is use temp to store the results of each thread, and then we have to decide that the special thread 0 will be the one in charge of doing the sum that we saw earlier, right? So, okay, looks fine for you. Yeah, seems fine, seems nice. Okay.
Why the thread 0 is the last executing, I mean, at the if, they must have finished it.
Right.
So,
So is that true? No. I think you were pointing to the right. You were, no, thank you for doing that. You were pointing to the right problem. Question is, will all threads be ready when the first one arrives to this point? And the answer is no. It may happen, but it may as well not happen. So, again, you cannot decide which thread will be executed first or last, but you can synchronize them with the function call which is sync threads. Okay? And well, the problem is evident to everybody, I think. So in the version that we had before, if threads 1 sorry, let's make thread 2 be late, and so thread 2 has not yet completed this operation, so it hasn't stored the value in temp, but thread 1 starts summing up the results. Okay, the sum will be just wrong. Is that clear? Okay, fine. That's why we need sync threads. This will guarantee that all threads are synchronized when this is called, and at this stage we can actually sum. But remember that threads are only synchronized within one block. So this works, but we are doing the dot product with just a few elements. So we have to repeat this with blocks. How do we do this with blocks? Like this, right? We have already introduced how we can make an index which runs on all the elements using both threads index and block index, right? And we exploit the same strategy that we used before. So we have many blocks running now, okay? But all blocks have different temp variable, right? So even if there are always 512 threads in each block will have a separate temp array, and that's fine, or at least seems fine, but
We have to synchronize the blocks.
exactly, but we cannot synchronize the block. And that's why so these blocks will run how they want, and there is no way to synchronize the block. What you have to do is to replace the sum, and CUDA provides you a set of atomic operations. So atomic operations are the way you interact with the way you avoid data races with blocks. So there are a number of these atomic operations that start with atomic plus add, sub, mul, and you can check them on the documentation. And these are guaranteed to read, modify, and write the variable here, the global variable here, with the value that you give as a second argument in a thread-safe way out of multiple threads in the execution. So when you are doing so, you have a operation that is safe to do with the threads of the different blocks. Okay? Okay, so I think that this first introduction should give you all you need to start changing the main.c of the CPU code and rewrite the two compute intensive parts in CUDA. First question is, what are the functions that you should focus on? Have you played a bit with the exercise, right? So there are mainly two functions that we have described this morning at the very beginning. One is the one that creates the random points in the box, and the other one is one that counts them. So you immediately see that these two functions resembles the one that I introduced here. One is completely independent computations, right? So all the points in a list should be moved to the box. So what you will have to do is to allocate some space on the GPU, collect random points, then move all of them in the box. And this operation for each point is independent, right? So this is simple and looks like the add that I introduced at the beginning, while instead the second operation is counting the hits. And you see that if you do this for a large number of points, at a certain point you will need to do a reduction, right? So for a set of points, you will have to sum all the points that actually hit a circle and provide that as a result of your kernel. So this is the task that be done for the next hands-on. There is just one more thing. So as you probably have noticed, the memory on the GPU is much smaller than the memory on the CPU, right? So you may end up, so the size that I gave you is correct for the amount of RAM that you have on the GPU. But if you start increasing it, you will soon finish it. And if all of you start using the same GPU, you will soon find that there is not enough space for allocating the data. So I'm sorry, but I fear I have to briefly introduce this. So as I told you, you can develop on the login node. So you can maybe shrink the dimension of the arrays of the main.c to make it simpler to allocate on the to make it simpler for your colleagues to work on their code and avoid allocation failures. You may also want to set different devices, and you can do this with these APIs. So you can just select if you want to use the first device or the second device with this set of instructions. It makes it easier to avoid all of you clashing on the same GPU, which is device 0, and fill its memory, because you are 30 and this may happen. So at least if you split the two devices we have on the login nodes, and if you work on the compute node together, you split the device that you have there with this set. You just have to put this at the very beginning and at the very end of your code. But okay, so I think we can introduce this later. What time is it? Okay, we have a quarter of an hour. Questions on the things that I introduced till now? Yes.
Are those slides online?
I will upload them as soon as I finish talking, and so you can just. But the code of the slide. No, there is the OpenSCC code. No, I will upload them. Yeah, in a minute, and so you can just go through them and copy paste what you need or refer to them when you do the hands-on. Yes.
The pieces of code that you showed before, you defined something like the number of threads or the number of blocks.
Yes.
But this may make the code dependent on the CUDA device you're using. The
Yes.
physical device.
Yes. You are correct.
Any way to make it general for every kind of physical device you use. Like there is some function to get the number of blocks or threads within.
No, this is the wrong terminal because it's a small one. But I'll try to make it bigger in a second. Okay. I make it bigger in a second. Sorry about that. Oh, where was it? Ah, here it is. Like this should be enough. Oh, like this is too much. Let's try like this. Can you read it? Okay, fine. So let me go quickly back. I logged in on Galileo. I loaded CUDA 9. I executed device query. Now, if you look what device query is, it's just a piece of code that stays here. CUDA toolkit, samples, bin, compile, Linux release, dev, whatever. So this is a piece of code that you actually have, and you can actually see what it is. So if I do, I know I'm taking a long path to answer your question, but I think it's worth it. So here you have, no, this is just the compiled version. Samples, 1, utilities, device query, shit, device query.cpp. Yeah, here you have the code of device query. This is the code that, don't read it. I mean, it's just like the code that you can read, that you can check out. And this code is what prints this, right? This is the output of device query. Device query is the command at the very top. So device is starting, detected 2 devices, okay. So you have capabilities, but as I promised at the very beginning of this lecture this morning, let's go have a look at the outputs that it gives. It gives a lot of information, but if we go, well, yeah, compute capabilities, memory, and if we go a little bit down, and if you look here, voila, maximum number of threads per block, okay, and maximum size of a grid. A grid is the size of blocks, right? So the max dimension. So this is the maximum size of the. So the number of blocks that you can have The grid is the distribution of the block. And to answer also your question, it depends on the hardware. Yes. How do you make a code that is not dependent on the hardware? You query these numbers and you react accordingly. Okay? So, hope this answer was a long way, but this tells you. And yes, and there is also another important thing that you may check, yeah? And is this one, compute mode. Multiple host threads can use the same device simultaneously. This is what allows us today to do the hands-on all together on the login node. Otherwise, you may see errors telling you that device is not available. So there are no devices available for you to execute or test. And if you see something like this, you may check how is this setting on your system. Okay, so I think if there are no other questions, I don't know if we can finish a little bit earlier or just introduce the hands-on now very briefly, and then we can finish a bit earlier and start a bit earlier. Is it fine for you? Fine for all of you? Great. So keep everything in the same window, time window. Okay.
Quindi il numero di blocchi, in quel caso lì era 216 per...
Il numero di blocchi dipende dalla dimensione.
Beh, simmetrico per
X per Y per Z.
Sono